Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues, I hereby formally open this session, and I welcome you all to the public defense of Marrick Braam. I'm Christine Kirschhock, and I have the pleasure to lead you through the ceremony today. This thesis is the result of a collaboration between the University of Edinburgh and KU Leuven, and the candidate will receive a joint degree from both institutions, should the jury decide so. Marrick already had successfully defended his thesis at the University at Edinburgh, and that on May the 10th. Now, it's time that the candidate also fulfills his obligations to KU Leuven. To the Faculty of Science of KU Leuven, Marrick Braam has presented his PhD thesis on the topic, The Atmospheric Chemistry of Earth-like Exoplanets, a 3D Perspective. And this in partial fulfillment of the requirements for obtaining the degree of PhD in science, astronomy, and astrophysics. Marrick started his journey into exoplanet science with a degree in astronomy at the University of Groningen. His fascination was initiated by a research project exploring criteria for habitability of rocky exoplanets. During his master project, he worked on the spectroscopic characterization of exoplanet atmospheres. And following this, Marrick began pursuing a joint degree of Doctor of Philosophy at the University of Edinburgh and KU Leuven, and this in the frame of the European Chameleon International Training Network. Marrick, you now shall publicly defend your PhD thesis. You are invited to give a presentation of about 45 minutes about your work. And afterwards, the jury will have the opportunity to discuss with you. The floor is yours.
Thank you. Thank you, Christine, for this lovely introduction. Thank you all for coming, and online viewers, thank you for coming as well. So it's my pleasure to present my PhD research. Before doing so, I want to say a big word of thanks to Professor Leen de Sin for supervising me throughout this project, and Professor Paul Palmer as well, who's joining us online today. The work I'm presenting was done as a wider collaboration, and a big word of thanks also has to go through the Exeter Exoplanet Theory Group and the Chameleon Network that Christine also introduced. So I want to start with a little introduction to exoplanets, and no exoplanet talk can start without mentioning how many exoplanets we've discovered nowadays. So there you go. That's the number of exoplanets that we know of. I've plotted them here in orbital period versus planetary mass space, as compared to solar system planets that are indicated by the letters over here. And this horizontal line over here is a crude dividing line between gaseous planets and rocky exoplanets. I am mainly interested in the rocky exoplanets, so mainly the population that you can see over here. And these are most easily observed around so-called M-type stars, which are, as you can see here, smaller and cooler than the sun. So the sun is here at 5,800 Kelvin. and M stars are all the way down here, around 3000 Kelvin. Now you can see on this plot as well, planet Earth nicely orbiting in the so-called habitable zone, which is the circumstellar zone in which liquid water could exist on planetary surfaces. Once we move to the M-type stars, you can see that this habitable zone moves inward quite substantially, and therefore any planet orbiting in the habitable zone around M-dwarf stars orbits very close to the host stars. This leads to a strong gravitational interaction between the two, which can lead to a situation that is known as tidal locking, where you have a synchronization between the planet's spin around its own axis and the planet orbit around the star. We can use this simple formula that relates planetary parameters, so the orbital distance, planetary density, stellar mass, and these two parameters over here that indicate the interior structure of a planet, to actually calculate the amount of time a planet needs to be synchronized. So I've done so for the planets that you can see in the plot here. And now you can see that the blue dots indicate planets that have a tidal locking timescale that is larger than 1 gigayear. The orange dots here indicate planets that have a tidal locking timescale less than a gigayear. And if you compare this to the age of the solar system, 4.6 gigayears, then this is a rather short time. So a lot of these planets may have been tidally locked throughout their evolution already, and therefore orbit in so-called spin-orbit resonances, where the exact spin-orbit resonance depends on the planetary eccentricity. So this has important implications for a planet itself, because if you compare the Earth's orbit around the Sun, you can see that it spins a lot of times, 365 times around its own axis, for every orbit around the star. Once we move to these one-to-one spin-orbit resonant planets, you can see that these orbit once around their own axis, spin once around their own axis for every orbit around the star, and therefore have a permanent day-side and night-side hemisphere. There are higher order resonances, and an interesting example of these is the 3-to-2 spin-orbit resonance, where the planet spins around its own axis 3 times for every 2 orbits around the star. So in this case, after every orbit around the star, you have a change in daytime hemisphere. And here you can see, well, maybe hard to see, but this is actually an orbit with an eccentricity. So there's Apoastron, the farthest distance from the star over here, and Periastron on the other side. And you may think that this sounds exotic, but we do actually have nearby examples of such spin-orbit resonances, which is first the Moon orbiting around the Earth in a one-to-one spin-orbit resonance, and secondly, all the way on the bottom right, Mercury orbiting in the 3-to-2 resonance around the Sun. Now, a lot of work has been done already investigating the atmospheres of planets in one-to-one spin-orbit resonances. And what this implies is, of course, day-side, night-side hemispheric contrast, because radiation comes in on the day side over here. Therefore, you have a warm day side with potentially energetic processes, as well as drivers of atmospheric dynamics and chemistry. Whereas on the night side, no radiation comes in, and therefore this is relatively cold, and any chemistry that is happening here will mainly be dynamically driven. In studying this chemistry on exoplanets, we can take several approaches, increasing in terms of their complexity. So the easiest way to approach this is simply to model chemistry as a function of the atmospheric temperature and pressure, which we would call equilibrium chemistry. But as we know from Earth, there is a lot of processes that actually affect the atmospheric composition. One prime example is, of course, life on our planet. But other examples include the interaction with stellar light or photodissociation, the impact of stellar flares, lightning, atmospheric dynamics, volcanism, or even meteorite impacts. These could all drive atmospheric chemistry out of its equilibrium state. So it's maybe helpful to discuss what the vertical structure of a planetary atmosphere would look like. So we can see here is the pressure decreasing with altitude, and then this black line indicates a more or less general temperature profile, where you can see tropospheric regions between 1,000 and 100 hectopascal, with temperature decreasing as a function of the pressure. So this is where processes like convection and consequently cloud formation can happen on a rocky planet. If you move a bit higher up, you can see here that the stratosphere starts, and no longer you have this decreasing temperature with altitude. So this layer is actually stable against convection. This region is very important because, as we know from Earth, this is the region where UV light, indicated by this light blue line here, is actually absorbed and can drive photochemistry. Moving to higher layers of the atmosphere, even more energetic radiation is absorbed and can drive ionization of chemical species, for example, but this will not be treated throughout this talk here. Now, at the very start, of course, you saw that I'm discussing Earth-like atmospheres, and one can ask, what does an Earth-like atmosphere actually mean? And there's quite some discussion about that, but how I define an Earth-like atmosphere here would be an atmospheric or a surface pressure like what we have on Earth, so 1,000 hectopascal or 1 bar surface pressure, and an atmospheric composition that is dominated by molecular nitrogen, oxygen, carbon dioxide, and water vapor. Inside such an atmosphere, there are several chemical processes that are important to consider. Firstly, this would be the so-called Chapman mechanism of ozone formation, where photolysis of oxygen drives the formation of ozone, as you can see on the upper right here. Once formed, this ozone can be destroyed by so-called catalytic cycles. The first one of these is the hydrogen oxide catalytic cycle that results from the presence of oceans on a planet, from which water vapor can evaporate, and this water vapor can be photolyzed or oxidized to form these Hox species, such as the OH radical. On the other hand, if lightning flashes are present on a planet, then the high temperature channels from these lightning flashes have sufficient energy to break the molecular bonds of nitrogen and oxygen, and thereby produce NO, which is another radical species that can drive the nitrogen oxide catalytic cycle, and in this way also destroy ozone. On Earth, this leads then to, well, these are the main processes that lead to an ozone distribution that you can see over here. I should say this is the vertically integrated amount of ozone molecules. So if you would travel through one layer of the atmosphere upwards, this would be the amount of molecules that you encounter. And then ozone can both be in the stratosphere, where it's good for life because it absorbs harmful UV radiation that would otherwise negatively impact life on the planet. However, once ozone is found in the tropospheric regions, it can actually be harmful to life in itself. One thing you can note from this figure is actually that there's quite some spatial structure. So around the equator, which is the outer ring, you can see a relatively thin ozone layer, whereas you can see more or less accumulation of this ozone once you move to the higher latitudes, so over the North Pole, for example, here. Since we've mentioned before that ozone actually formed as a product of photolysis, it needs stellar radiation, and therefore its production is mainly limited to the regions around the equator, as shown by this yellow square over here. What happens subsequently is that there is a stratospheric circulation mechanism that drives ozone from the equatorial regions towards the higher latitudes, where it actually subsides and thereby regionally enhances the ozone layer at the higher latitudes. And this mechanism is known as the Brewer-Dobson circulation on Earth. So given this background, given this 3D structure that we see on Earth, we asked ourselves the question, what would be the impact of spin-orbit resonances on the atmospheric chemistry of such Earth-like exoplanets? I will consider 2 planets throughout this talk. Firstly, Proxima Centauri b, which is the nearest known rocky exoplanet to Earth. So in that sense, already an interesting example. And on the other hand, there's TRAPPIST-1d, which is one of the planets of the well-known 7-planet resonance chain with potentially a few habitable candidates around star TRAPPIST-1. To study these processes, what we need is, of course, a 3D model. So I will start by introducing the model that we're using, the so-called coupled climate chemistry model, discuss its application to atmospheric photochemistry, to wind-driven ozone chemistry, lightning-induced chemistry, the effect of the higher order resonances on the chemistry, and finally discuss some potential observable observational consequences. So the model I'm using, it looks a bit low resolution, but okay, is the so-called unified model, which is the climate model that is owned by the UK Met Office and commonly used for weather and climate prediction on Earth. We use this in its coupled version to the UK Chemistry and Aerosols Framework, which is one of the leading 3D atmospheric chemistry models on Earth as well. Such CCMs simulate the 3D climate, the dynamics, and the photochemistry on this spherical envelope that basically represents the atmosphere. So you divide up the atmosphere in grid boxes, horizontally using latitude and longitude as coordinates, and vertically using height or pressure as coordinates. And then in each of these grid boxes, you solve for processes such as radiative transfer, the exchange of water vapor between the surface ocean and the atmospheric dynamics, cloud formation, and so on and so forth. Whereas on the other hand, the chemistry scheme also computes the interactive photo and kinetic chemistry all around the planet. So as said, I use this Earth-like atmospheric composition as a starting point, and I consider full aquaplanets. So it's a planet that's completely covered by an ocean instead of having this Earth continental distribution, as you can see over here. And what we usually do with such models is that you specify a certain initial condition, and then you run the model to a so-called steady state in which important atmospheric parameters don't change too much as a function of time anymore. And most of the results I'll be showing are from this steady state, but at a few occasions, I will also use part of the so-called spin-up, which is then the initial run of the model, to probe, for example, atmospheric dynamics. Now, the most important thing, if you move such an Earth system model to the study of exoplanets, is, of course, the change in stellar radiation. So what you can see up here is the comparison between the radiation that Earth receives from the sun, peaking at visible wavelengths, as you can see over here, and the radiation that is received by Proxima Centauri b for two different spectra, and by TRAPPIST-1d, where you can see that this light is more concentrated towards higher wavelengths, towards the infrared. Now, I should say that this builds upon previous work that was done by Jack Yates et al. That actually used this BT settle spectrum, so the Cyan line that you can see over here, as a first study of the chemistry of Proxima Centauri b. We updated this study by actually using the so-called muscle spectrum, which is the darker blue line of Proxima Centauri b. That's more of a... So the initial spectrum that was used was purely a modeled stellar spectrum, and this muscle's stellar spectrum is actually more based on observations of the star itself. If we zoom in on this lower wavelength region over here, we can see the regions that will be important in the consideration of photochemistry. And then you can see, comparing the different lines, that there's quite some differences between each of the stellar spectra, which will be important for our formation of ozone later on. Before diving into the results, there is one more topic that I have to introduce to you. And I always like introducing it because it's a very counterintuitive thing. But this is introducing different coordinate systems. So what we are used to from Earth is the so-called geographic coordinate system, where latitude 0 corresponds to the equator, latitude 90 and minus 90 correspond to the poles. And then longitude is the angle around the equator with a kind of arbitrary 0 point at Greenwich, I think. Now, if you use this coordinate system for planets in a one-to-one spin-orbit resonance, both the substellar point and antistellar points are kind of random longitude points on this grid as well. But because of the symmetry that you see on these planets, so these day-side, night-side differences, it can actually help to move to a so-called tidally locked coordinate system, where you kind of just flip the planet, and in this way have tidally locked latitude defined as the angle that you can see over here. So basically, the terminator region, the boundary between day side and night side on the planet, is the 0 degrees latitude, whereas the substellar point and antistellar point are at plus and minus 90 degrees in tidally locked latitude. And then, what is very useful is that, as you can see on the right here, that tidally locked longitude actually provides lines between the substellar and the antistellar point. So the tidally locked longitude is now the angle around the terminator, and any line of constant longitude connects substellar and antistellar point. And this will be useful in actually probing atmospheric dynamics between the 2 points. I hope that makes sense, but I think in most plots of the one-to-one spin-orbit resonant planets, I've indicated where the star is located, which has helped me a lot over the years, and I think might be useful in this case as well. So to start with the photochemistry for Proxima Centauri b in a one-to-one spin-orbit resonance, you can see on the left here, temperature distribution, and as said, the star is indicated over here in the geographic coordinate system still. You can see a warm day-side hemisphere and a cold night-side hemisphere with especially cold regions over these so-called night-side gyres that are basically, you can see from the wind factors, these arrows represent the winds, that over these regions, air is basically trapped, radiatively cools, and thereby provides the coldest places on the planet. The white line over here denotes the freezing point of water. So you can see that inside this white line, approximately half of the day-side hemisphere is above the freezing point of water, which some might consider important for habitability. Now on the right then, I show the transformation to tidally locked coordinates, and once again indicating the star. So as said, the star is now at 90 degrees in tidally locked latitude. So instead of having stretched poles, which would normally have in your coordinate system, the star is now stretched because of the 2D representation of a 3D model, of course. Then you can see the terminator nicely at 0 degrees latitude, and you can see that these lines of tidally locked longitude nicely connect the substellar with the antistellar point. But outside of that, the features are the same, as should be as well. If we look at the ozone layer around this planet, so you can see on the right here, once again, the ozone column density, so vertically integrated, once again, the same as what I showed for Earth. Then you can see that there's a relatively thin day-side ozone layer, and that there is this accumulation of ozone over the night-side gyres. This agrees with earlier work by Jackie Yates et al., but our change of stellar spectrum led to a tenfold increase in the thickness of this ozone layer, basically planet-wide. And if we look at the vertical distribution of this ozone, you can see here that this stratospheric ozone layer nicely forms over here, and down here between tidally locked latitude 0 and minus 60, and at pressures higher than 100 hectopascal, this is your gyre accumulation. So this is where the gyre enhancement of ozone comes from. Now, of course, we said before that ozone needs photochemistry to be produced. So you can see this red blob presents a positive balance between the chemical production minus the chemical loss of ozone. And so you can see that ozone is mainly produced in the day-side stratosphere. So the fact that it's produced here, accumulates over here, indicates that there should be some kind of connection between these two regions. And to look into this, we used some atmospheric dynamics theory, which required me a lot of reading introduction before I could even understand this. But I think I got it now after a couple of years. So what I show you over here is the so-called stream function. In this case, the meridional stream function in tidally locked latitudes. And I think because of the name, you can understand already that it's quite a tough concept to understand. It's given by this formula, but it's not very important. What is important to know is that in this plot where there is positive values, this means that there is a clockwise rotation of air, as indicated by the arrows over here. Whereas when this is negative, you have an anti-clockwise rotation of the air. So then you can see that in the troposphere, so between 1,000 and 100 hectopascal, there's actually a strong transportation, a strong transport cell, basically, circulating air and as well as heat from the substellar point all the way towards the night side, which is good. That's what was shown earlier as well. What we are interested in, of course, is the circulation of ozone itself, whereas the stream function before showed the circulation of all air that's in the atmosphere. So what we did was to simply multiply the normal stream function by the ozone mole fraction, which is the amount of ozone divided by the amount of air, and which you have all around your planet as well. So this simple multiplication just gives you how much ozone is being circulated all around the planet. And then you can see that, well, there's still this tropospheric cell, but now there's also a strong stratospheric component to the circulation that is almost equal in strength to the tropospheric cell that we saw down there. So this could maybe provide a connection between the ozone production region in the dayside stratosphere and the gyre accumulation on the night side. To probe this a bit more, I extracted pressure levels between 200 and 8 hectopascal to actually calculate vertical fluxes of ozone, which is using the vertical winds in the atmosphere times ozone number densities, and then integrating this over different pressure levels. And from the vertical wind then follows, if this is positive, it means that there's an upwards flow of ozone. When this is negative, it means that there's a downwards flow of ozone. And you can see the evolution over time in the plot on the left, where the mainly positive values in the dayside hemisphere indicates that there is ozone transporting upwards in the atmosphere. Whereas if you look at the gyre regions, you can see that there's predominantly downwards flow of ozone, which nicely aligns with the time evolution of the gyres, as you can see on the right here. There's one more way in which you can probe this, which is actually using the spin-up of the simulation. So these are the very initial stages of the simulation from rest, basically. So you can see that at day one, you can see from the distribution of ozone over here that ozone is mainly found in the dayside stratosphere. So this is where it starts to be produced. And if we then play this video as a function of time, you can see that it starts to fluctuate, starts to transport towards the night side, where it in the end accumulates in these gyre regions. So this once again indicates that there is this stratospheric circulation that is driving the ozone from its dayside production regions towards the gyre accumulation. And we've termed this the stratospheric, very nice way to pronounce it, actually. The stratospheric dayside to nightside circulation. We should have come up with a better name now that I see it, but it's too late for that. And you can see it summarized once again over here. So ozone is produced on the day side, circulates towards the night side, where it starts to accumulate in the gyres. So that was the example of wind-driven chemistry around the planet. And now I want to discuss lightning-induced chemistry on this same planet, which was motivated by the fact that, okay, well, you can kind of see it, right? This is all right? Okay. Well, it was motivated by the fact that I show you here some plots from a model into comparison, with the top row showing cloud water path and the bottom row showing cloud fractions. And across a range of different 3D climate models, well, you can see there's differences between them, but one common feature is that in all cases, the dayside hemisphere, centered at the star over there, is covered by this thick convective cloud deck. And if you think about thick convective clouds on Earth, well, not everyone might think that way, but some people might also connect this to the presence of lightning in these thick convective clouds. And it has been shown by previous work that the process to generate lightning in a planetary atmosphere is similar across different planetary environments, also motivated by the fact that we have detections of lightning on Jupiter, Saturn, and Venus. And I may be forgetting one now, but I think those three are the ones that have confirmed detections. And of course, as I discussed before, there's this role in atmospheric chemistry and a potential role in prebiotic chemistry, which are the famous Urey-Miller experiments that make this a fascinating topic of study in the sense of in the context of exoplanets, of course. So what we did was to use quite an old scaling relation, initially derived from Vonnegut, which I think is the brother or the uncle of the writer that some of you might know as well, who actually derived scaling relations by considering a cloud, as shown over here, to be a dipole structure with one charge at the bottom of the cloud and a charge at the top of the cloud. And therefore, the separation between the two determines how much electrical power is available in this single cloud. So based on this, you can derive an amount of lightning flashes that can form from this total amount of electrical power that you have available. And therefore, you can parameterize the amount of lightning flashes in terms of the cloud top height. And of course, this is true to Earth, but it's a very simple parameterization that is a nice one to make a first application to exoplanet environments as well. So that's what we did. We did this for Proxima Centauri b in the 1-to-1 spin orbit resonance. And here you can see the formation of lightning flashes on a daily basis in this simulation of Proxima Centauri b. So the flash rates are not particularly high, basically similar to oceanic flash rates on Earth, which is what we would expect given that we have an ocean-covered planet as well. And generally, lightning flashes are more prevalent over land on Earth. But an interesting thing that you can see here is that the lightning flashes are concentrated over and around the substellar point, whereas basically no lightning formation happens once we move to the night side of the planet. So this is, again, a 3D distinction between the two, which, as we said before, might have some implications for the atmospheric chemistry as well. So we included a production of NO per lightning flash because of this reaction as shown over here. And then from this figure on the right, you can then see that this NO, once again, a vertically integrated amount of NO molecules in this case. You can see that NO starts to be produced over and around the substellar point and quickly spreads around the day side of the planet as well. From the vertical distribution that you can see over here, this NO, due to lightning, is mainly concentrated below 20 kilometers in altitude, which is where our clouds would form, where the lightning would happen as well. And if we look over time at this NO, you can see that following the day side spread, there are these outflows of NO towards the night side of the planet. But if we keep looking first on the day side of the planet, in the presence of stellar light, NO can quickly react with ozone, actually, to form NO2, for which you can see the distribution in the bottom plot here. So once again, this NO2 is also mainly found on the day side of the planet. And this relative hemispheric difference gives the day side average minus the night side average divided by the global average. When this is positive, this just means that there's more of a species on the day side. When this is negative, there's more of a chemical species on the night side of the planet. And then this forms part of a chemical mechanism all around the planet, where the lightning produces NO, reacts with the ozone to form NO2, and on the day side, this is photolyzed back into NO. So you have the balance between the two on the day side. Now, as we move towards the night side, of course, there's no longer any stellar radiation present, so this step back to NO will not happen anymore. And instead, what NO2 will do is to react with other species, the OH radical, NO3, or ozone, to form these more complex, they call it nitrogen reservoirs, because they have a very long lifetime on the night side. And you can see from the horizontal distributions and from this negative hemispheric difference, indeed, that these species are mainly found on the night side of the planet. So this then basically shows you that you have this 3D distribution, which of course firstly depends on the presence of lightning, but then starts to also have this coupled interaction with the atmospheric dynamics and the photochemistry, and thereby provides these nice 3D connections all around the planet. Next up, I want to discuss TRAPPIST-1D in a one-to-one resonant orbit at first as well, which was deliberately chosen because it's known from previous work that Proxima Centauri b and TRAPPIST-1D for a one-to-one resonant orbit show different, what we call circulation regimes. And for Proxima Centauri b, this is mainly characterized by this equatorial jet. So you can see this wind structure flowing all around the planet in the equatorial regions. For TRAPPIST-1D, what instead you see from the arrows is two mid-latitude jet structures. And this is mainly connected to their slightly differing orbital periods, and in this way, rotation rates around the planet, around the star. Now, for TRAPPIST-1D, we found some interesting unintended results, which you can see from this red line over here, where temperatures quickly started increasing from, 280 till 340 Kelvin, after which the model crashed, which is very disappointing at the start and can be frustrating from time to time as well. But once we thought about it a bit more, it's actually quite an interesting case in itself. Because this might indicate that TRAPPIST-1D exhibits the so-called runaway greenhouse limit, where if you have a planet with a lot of water on the surface, this water will evaporate and water will act as a greenhouse gas, thereby warming the surface again. A warmer surface will lead to more water evaporation, a stronger greenhouse effect, and so on and so forth. So it's basically a cycle that keeps continuing until the planet warms so much that at least the model can't do it anymore. I'm not sure what will happen in reality exactly, but the model doesn't like it so much. And you can probe this runaway greenhouse through looking at radiative balance, so the balance between incoming radiation and outgoing radiation, which, as you can see, is quite positive for TRAPPIST-1D, and therefore indicates that there's much more radiation coming in than going out. And previous work gave some limits in outgoing radiation, so the radiation emitted by the planet, and stratospheric water vapor abundances. And for both limits, so the 280 watts per meter squared in outgoing radiation and stratospheric water vapor abundances of 10 to the minus 3, you can see that this simulation crosses both these boundaries. And therefore, again, this seems to indicate that this runaway greenhouse state is reached. So what we did was to artificially reduce the incoming stellar radiation, which I think some people discuss as an option for protecting planet Earth as well. I wouldn't recommend this, just to say, but it's still an interesting experiment in the context of exoplanets. And then you can see that the evolution of these different parameters is given by the blue lines, and we have a stable climate state, at least, in our simulations. And then you can see the resulting temperature profile on the left here. So a very warm dayside hemisphere, and also quite a substantial fraction of the nightside hemisphere is above the freezing point of water. And on the right, you can see from the ozone column density that what we have now is a relatively thin equatorial ozone layer and an accumulation of ozone at the higher latitudes. And note that this was different for Proxima Centauri b, where we instead saw the nightside accumulations. So it's longitudinal variations on Proxima Centauri b, latitudinal variations on TRAPPIST-1D. And well, it wasn't too unexpected now, of course, that this was once again related to the wind-driven chemistry. So you can see here the vertical distribution of ozone, and its evolution over time shows that it's too quick. It shows that it's produced around the equator at the start of the simulation, and then starts to spread towards the higher latitudes, basically indicating this equator to pole circulation, reminiscent of the Brewer-Dobson circulation that we saw on Earth. Now, next up, if we move to the higher order resonances, we will start again with TRAPPIST-1D because it was still being annoying. Because now I added this pink line to the evolution of climate parameters over time, and you can see that even faster it goes into this runaway state. Also as probed by radiative balance or disbalance, as probed by the outgoing radiation, and lastly by stratospheric water vapor abundances. And I said that this was annoying, but it's kind of interesting in itself again, because this seems to indicate that there is some kind of climate sensitivity to the exact orbital resonance state that a planet is in, with having a stable climate for the 1-to-1 resonant case and then going into runaway for the 3-to-2 resonant case is an interesting result in itself, and might have some implications for the inner edge of the habitable zone, so where planets can remain in a temperate climate, basically. And we found that this is mainly driven by the fact that these 3-to-2 resonant orbits require a certain eccentricity to be stable. But I'll get back to that eccentricity in just a little bit. Because Proxima Centauri b actually allows for a stable climate still in the 3-to-2 resonant case. So you can see the time evolution of the surface temperature on the right here, with daytime on the 180 degrees hemisphere, later on daytime on the 0 degrees hemisphere, and so on and so forth. So this is basically, this just repeats itself. And notably now, we once again have a temperature gradient with warm equatorial regions and colder polar regions. So some of you might be able to predict this now already. What we see for ozone is similar as what we saw before as well, a thin equatorial ozone layer and an accumulation of ozone at the higher latitudes, which I don't even have to show anymore, I think, is caused by this equator to pole circulation. Following the production around the equator, ozone starts to flow towards the higher latitudes where it subsides. And therefore, again, you have this this Brewer-Dobson-like structure in the atmosphere, in the atmospheric circulation. Now, the 3-to-2 resonant orbit comes with some more interesting implications, due to the fact that this planet, of course, goes in cycles of periastron, closest distant to the host star, and apoastron, furthest away from the host star. And you can see these cycles in the black line here, which presents the global average of the incoming radiation. So this is minimum in apoastron, and there's a maximum amount of radiation coming in at periastron. Besides that, there is also, to complicate the picture a bit more, day-to-night cycles, because the planet now shows a changing daytime hemisphere, which you can see from these orange and blue lines, basically showing that there's first daytime on the 0 degrees hemisphere, then on the 180 degrees hemisphere, and this repeats itself on and on. Now, these cycles are also seen in the surface temperature, probably as we would expect. So maximum surface temperature on the dayside hemisphere, slightly after periastron, and minimum temperatures around apoastron. And in this black line, you can clearly see the periastron-apoastron cycles in the global incoming, or the global surface temperature as well. Water vapor column densities follow this trend of the surface temperature, because of course these two are once again connected as well. So we have the most water vapor in the atmosphere slightly after periastron, whereas the lowest, and then on the day side of the planet, obviously, whereas the lowest amounts of water vapor are on the night side hemisphere just after apoastron. Lastly, the ozone column density shows a very weak trend in the global average. So the periastron-apoastron cycle is almost negligible, which is due to the fact that ozone has a longer chemical lifetime and therefore takes some time to adjust to these radiation changes. But you can see that there's still a daytime-nighttime cycles, with ozone columns being thickest on the nighttime hemisphere and thinnest on the daytime hemisphere. And this is then connected, this opposite behavior to the water vapor column is then connected to the catalytic cycles that actually provide more ozone destruction on the dayside hemisphere as compared to the nightside hemisphere. And these cycles in themselves are interesting from the perspective on life on other planets, because of course, life on Earth needs, for example, these wet-dry cycles to exist. But also the origin of life is thought to require these so-called wet-to-dry cycles to occur in the first place as well. So if this 3-2 resonant orbit can naturally give these wet-dry cycles, that would be an interesting topic for further study. And some previous work has proposed seasonally varying chemical species as biosignatures, or signs of biological processes on other planets. But if, as shown, a planetary orbit can naturally provide such seasonally varying chemical abundances, then this allows for some interpretation once again, as if we didn't have enough interpretation for biosignatures yet. So lastly, I want to go into some observational consequences of this 3D atmospheric chemistry, and I'll specifically focus on Proxima Centauri b. And I'll consider emission of the planet itself. So here I compare the emission from the sun, peaking in the visible at very high amounts, as compared to a planet that, of course, emits light itself as well, but at longer wavelengths, so more towards the mid-infrared of the spectrum, and of course, at much smaller amounts. But the fact that the peak of a planet like Earth is found in this mid-infrared region makes this quite an interesting wavelength region to actually probe exoplanets emission directly. And a good example is, so this is a picture taken from around Saturn of what you can see here, planet Earth. And you can see it emits some light, of course, but this light varies quite a bit as a function of wavelength. So you can see at the very short wavelengths, this is mainly reflected stellar light, but you can still see planetary features such as oxygen, ozone, water vapor in this reflected stellar light. Once we move to higher wavelengths, we go more towards the mid-infrared and the emitted planetary light. And then especially between 5 and 20-something microns, you can see the direct emission from the planet, including features such as ozone, CO2, and water vapor. Now, the Large Interferometer for Exoplanets is a proposed mission concept for an ESA L-class mission, I think it was, that actually intends to probe these thermal emission spectra of exoplanets using a combination of 4 telescopes in space that you connect as an interferometer to assess diversity of planets, potential habitability, and to search for possible biosignatures on these rocky exoplanets. Previous work has shown that it can detect water vapor, CO2, ozone, methane, no problem. And especially considering Proxima Centauri b, which is firstly, of course, the nearest exoplanet to Earth, and it orbits this M-dwarf star, so it's a nicer balance between stellar radiation and planetary emission, which makes this one of the prime targets for the LIFE mission, one of the most easily accessible rocky exoplanets. And previous work has also shown using real Earth observation data that actually Earth's mid-infrared spectrum varies as a function of the viewing geometry and the season on the planet. Now, temperature variations are detectable, albedo variations are detectable. No. Oh, it's up there again, no? Cool. Cool. All right. So hopefully I still convinced you that these variations are highly planet-specific. And that's why we wanted to translate this 3D simulations and actually simulated emission spectra, focused on the LIFE mission. And you can see over here, as a function of the orbital phase, that the planetary temperature or the side of the planet in a one-to-one resonant orbit varies quite a bit, depending on which orbital phase you observe this planet. We can compute synthetic emission spectra using NASA's planetary spectrum generator for each of these orbital phases. And then you can see from the plot on the right that there's, well, some can argue that it's not substantial, but that there is substantial variations depending on which orbital phase angle you observe the planet. So for example, water vapor features can vary by up to 30 ppms. And these features between 12 and 13 microns are more related to the planetary temperature. And you can see that there's tiny variations in the ozone feature, which, well, I would say these are probably not necessarily detectable, but some of these features might actually provide some variations as a function of time. And then, cool. You can also see that the strongest emission feature, or the strongest emission from the planet itself, is shown for the 32 degrees and 0 degrees phase angle, which is, of course, as you would expect, because these are when you probe the warmest sides of the planet. And then for the 3 to 2 resonant orbit, you can see that as a function of the phase angle, the temperature is more homogeneous as compared to the 1-to-1 resonance, and this also translates into more homogeneity in the emission spectrum. And this might actually be a potential discriminant between the two orbits if one shows these variation as a function of orbital phase angle and the other does not. So some work has been done, but of course a lot of work remains to be done, and I did want to give you a few potential avenues for future work. First one being more ozone chemistry, because as we know, for Earth, of course, over Antarctica, we have this big ozone hole, which I guess is less big than it used to be. But this was mainly driven by halogen chemistry, so chlorine, bromine. And this is something that has never been studied for exoplanets, even though they have these very cold night-side regions that might actually have similar chemistry going on. The impact of stellar flares is, of course, an important one around M-dwarfs, and has been studied in some detail already. Lightning parameterizations are used one. There are many, some more applicable than others. So we're currently conducting a comparison between these parameterizations to actually see which ones are better or worse, or whether they all agree. That would be great. Then in terms of habitability, so I've shown you some climate dynamics chemistry interactions for ozone and water vapor, but a lot more species could act as these radiatively active species, such as, for example, methane is an important one on Earth as well. And the sensitivity to the spin-orbit resonances, as well as eccentricity, has to be investigated in a bit more detail to actually fully understand the impact on the inner edge of the habitable zone. There is quite some opportunities in probing the prebiotic conditions, and specifically these chemical radiative or wet-dry cycles in terms of origins of life research on exoplanets. And lastly, of course, the spectra that I showed you were without any instrument noise. And before I can say anything about whether something is observable or not, we need to add some simulated instrument noise. So this is work that is still to be done as well. So I would like to leave you with a few takeaways that I've hopefully convinced you of. Firstly, being that stellar spectra are key in determining the ozone chemistry, and therefore to understand any chemistry on exoplanets, we do need to understand stars a little bit better, or at least know their spectra better. Let me put it that way. We find that lightning can be produced on the day sides of 1-to-1 resonant exoplanets with quite some substantial 3D variations in the subsequent chemistry. Circulation seems to be an important driver of 3D distribution of photochemical species. Like ozone, I've not shown any others, but the mechanisms also apply to other photochemically active species. Spin-orbit resonances can drive these, for example, wet-dry or chemical cycles, and have specific feedbacks to the climate themselves. And lastly, these 3D effects translate into spectral fluctuations in emission spectra. Thank you for listening, and I'm happy to answer any questions.
Marek, thank you very much for the very interesting and clear presentation of your work.
Thank you.
I think one take-home message is that we should take care of our climate, because you show sometimes a planet can get into a runaway mode.
Yep.
Now it's time
Definitely.
for you to defend your work. And we have a number of experts who are going to discuss with you. And unfortunately, most of them are attending only online because they couldn't make it here. So I will introduce each jury member when it's his time to discuss with you. And I suggest we are doing a small journey. Remember, your work has been done in collaboration between Edinburgh and Leuven. So let's start with the university in Edinburgh, then we take a step in Cambridge for the next examiner to end eventually here in Leuven. So I would like to welcome Dr. Trent Dubois of the Institute for Astronomy at the University and the Royal Observatory of Edinburgh. And he's an expert in brown dwarfs, exoplanets, low mass stars, and star and planet formation, and specifically specialized in observational techniques. Trent, please discuss with our candidate.
Yes, thanks very much. Okay, I'm getting a tiny echo, but that's all right. Marrick, wonderful talk. I guess I'll start with your first takeaway about the need for for understanding the spectrum of stars. I'm curious what you think. If you could tell, the only. It sounds like the region of wavelength that you need to know a lot about is the UV photons. And of course, so there's a whole range of photons going from sort of X-rays to the near UV that penetrates the Earth's atmosphere. So what's the most important, do you think, region of wavelength space to observe?
Can we show the slides once again? And thanks, Trent, for the question. It's a shame you couldn't be here.
British Airways fault.
Yes, we do have someone to blame here. So it depends a bit on the processes you're interested in, I would say, because so I think, okay, considering ozone chemistry in especially stratospheric regions, the region of importance is between this limit over here and maybe up to 500, potentially up to 800 nanometers. Because these
I can't see your pointer actually.
Oh, you cannot. Of course you cannot. I'm sorry about that. I will include a mouse.
Oh, there you go.
You can see this, right?
Yeah.
So between this lower limit here and between upwards to 500, maybe up to 800 nanometers, will be the most important regions for ozone photochemistry in the stratosphere of planets. However, in saying that you study ozone photochemistry in the stratosphere, you kind of make assumptions already about what is above the stratosphere. Because of course, there's a lot more radiation still below this lower limit here as well, which will be absorbed by the thermosphere, for example, and can drive chemistry over there. So in the context of ozone in the stratosphere, I would say the regions shown over here, especially these lower regions, because TRAPPIST-1d, as you can see from this line over here already, is not really fully correct. Let's put it that way. This is basically model derived from one measurement.
yeah, it looks pretty smooth. So that's probably, I guess, the model. So you're saying, so like, for example, the Lyman alpha photons that you get at slightly shorter wavelengths that you can see on the top panel, those don't penetrate enough to matter for your ozone production.
Those are the one exception. So the other radiation below, this is 177 nanometers, won't be too important for your photochemistry in the stratosphere. However, you're right for, well, you can see here TRAPPIST-1D, this Lyman alpha line, which is this large bump over here, can penetrate so deeply that it will affect the stratospheric photochemistry as well. So yes, definitely an important one to characterize and also to include, which has not, which is not included in the models that I've been using because this was an Earth-based model. For Earth, it's less important. For M dwarfs, for planets around M dwarfs, it becomes a lot more important.
This is very interesting. Do you know how much information we have on the variation in this, in the flux in this wavelength range? For these targets, especially. I imagine there's probably only been 1 or 2 spectra observed.
So you mean like variation between them or variation for one spectrum?
Sorry. So this is getting into, I think you mentioned at some point as well, the fact that these stars can vary in terms of how much flux they're putting out at any given wavelength. Observationally, from things like muscles and megamuscles, do we have good constraints on how much they vary?
I don't think necessarily from muscles or megamuscles, because these actually extract the spectrum in such a way that you have the quiescent spectrum. So you basically model out the effect of flares in them. But of course, isn't it, well, I'm not 100% sure, but I think TESS provides more temporal variations, for example.
Right. Yeah, no, I mean, you're right. I think you're right that when they observe, so I have HST on the brain just for reasons. Yeah, that they do separate out the flare spectrum from the quiescent spectrum, and and so for your work, you're using the quiescent spectrum. So this actually leads into the next thing I was going to ask about, which is, what about what if you threw in a mixture of flare and quiescent into your model? Is that's something that you could theoretically model, right?
Yeah, easily. No, not necessarily. But there is other work that was led by the group in Exeter, led by Robert Ridgway, who developed a new chemistry regime that can actually include this varying stellar output as a driver of the chemistry. And they have applied it to Proxima Centauri b, and actually finding that flares, surprisingly, could enhance the amount of ozone. So you produce more ozone after having a flare, so that in that sense, your planet is more protected from harmful radiation when looking at the next flare, basically. So it could still be harmful, but it can also help protect the planet, actually, against the impact of a next flare. Hope that answers it a little bit.
That definitely answers, yeah, exactly. So, okay, so basically, yeah, your code is, when I said it theoretically, I meant in principle, you could tweak the code to allow for changes in stellar flux, but yours doesn't do that, which is fine.
Yeah.
I mean, I think my final point on the stellar stuff is let's not think about photons, but just stellar winds or coronal mass ejections, that sort of thing. I mean, is that even feasible to include somehow in these models?
You really should have been here, actually, Trent, because there are some people in Lean's group actually that have worked on including this in models, which I don't think is necessarily the easiest when looking at the impact of exoplanet atmospheres directly.
What sort of impact, like even just a quiescent stellar wind from one of these things, does it have any impact? What would you expect it to have any impact on the chemistry?
I think it's mainly looking at atmospheric erosion, actually, whether you can actually keep the atmosphere under the impact of stellar winds. And I think that would be the first question to answer before considering whether it would affect the photochemistry.
Yeah, that's fair enough. I forget how much time. So I have a very naive question about your finding that, the 1-to-1 spin orbit resonance, when you go from that to the 3-to-2, is when you end up with this runaway state. Naively, does that imply that even higher order resonances, spin orbit resonances, would also lead to runaway, or is 3-to-2 like a special bad case?
This is purely speculating, but I would think that because higher order resonances, for them to be stable, they would require an even higher eccentricity than the 3-to-2 resonance. And this eccentric orbit is what drives additional radiation into the planet if you probe a full orbit, basically. So I would say, not knowing fully what the impact of the higher order resonance on, for example, atmospheric circulation, etc. is, but I would say purely from the orbital state, I would say yes, that probably drives higher radiative input, and therefore higher temperatures and probably a quicker runaway.
Okay, yeah, that makes sense. I forgot about the eccentricity part of it. Another thing I was thinking about with the 1-to-1, this is purely speculative on my part as well, way outside my expertise, but the moon is in a 1-to-1 spin orbit resonance with the Earth, so it rotates pretty slowly. Maybe that has something to do with why the moon doesn't have magnetic fields. Magnetic fields certainly play a role in habitability. Do you have any thought? Have you thought about this at all for these planets, or has anyone thought about this for these planets?
Yes, and so I have, well, of course I thought about it. I've not applied it, but I know of one work that has included crudely the effect of magnetic fields, which is the work by Howard Chen, where they basically, you assume that a planet either has a magnetic field or not, and in this way direct where the photons would come in and then interact with the chemistry, basically. So in this way, you can probe whether the photochemical effect of flares would be bigger or smaller, having or not.
Yeah, but so just the like the fact that the spin is connected to the orbit, which is connected to the likelihood of having magnetic fields. I mean, that's all just. Am I being too speculative?
That I don't know of any work
Yeah.
that has probably shown whether, for example, Proxima Centauri b could have a magnetic field or not. I'm not sure, but of course it is slow rotation, but it's also very close to its host star, so it does still rotate around its own axis. Well, I guess it's in 11 days, so it's not.
Well, it's faster than the moon. It's
yeah, exactly. Yeah.
Okay, I think I'm supposed to wrap up. I'm not exactly sure how long I've been going, but my last thing I was going to ask you about is the TRAPPIST-1D runaway. Your model kind of assumes the surface of the planet is entirely water, right? So
yes.
How much of the surface do you think you would need to turn into land to maybe get to avoid this runaway? I mean, is it possible?
Yes, that is definitely possible. So there have been some studies that use a full landmass around the planet, which of course leads to faster warming, basically. But indeed, as you say, because you don't have this reservoir of water vapor available, you don't have an infinite amount of water that can drive this runaway greenhouse effect. So you could prevent the runaway greenhouse effect by actually including some kind of landmass. Exactly how much that would be, and also the question, I think the main thing that prevents me from putting in land masses is the question of where do you put it? So I have some simulations that have this square landmass at the location of the substellar point, but it's not very realistic, obviously, to expect a square landmass there. But that certainly does provide less water vapor to the atmosphere, and especially because it's at the location of the substellar point as well.
Did you try? I mean, I feel like I remember we talked about this a little bit. Did you try running that one to see if it goes into Runaway?
Not yet.
Okay.
Not
Yeah.
yet. No. It's on the list.
Yeah. Yeah. Okay. I think I'm good to pass it over to my colleague.
Thank you.
Thank you, Dr. Dupois, for the nice discussion. And now we take a quick hop from Edinburgh to Cambridge. And let us welcome Professor Paul Rimmer, who also attends online of the Cavendish Laboratory of the University of Cambridge. And he's an expert in chemistry, primarily in the context of atmospheric chemistry and astrochemistry. And he has developed experimental strategies to simulate chemical processes on exoplanet surfaces and atmospheres. So please continue the discussion.
All right. Can you all hear me all right?
Yes, we can.
Excellent. I'm also getting a little bit of the feedback, so my question might be a bit halting. So you've shown some of the results of some quite formidable codes. I was wondering if you could just go in talking about some of the mathematics involved with some of these codes. These involve, first of all, solving certain equations to get the physics of the atmosphere. Could you talk a little bit about just the sort of number and the kind of equations that you're solving in order to do this?
Yes, I can. Thank you for the question. Unfortunately, I did not prepare a slide on this, which would have been quite useful, but I'll do it just like this. So indeed, this code itself is quite a complicated one because of the range of processes that you solve in one simulation, of course. So very fundamentally, what you start with is a so-called dynamical core, in which you solve the equations of fluid dynamics, which would be conservation of momentum, the conservation of mass or continuity equation, and connecting these two requires you to also specify the equation of state. And I'm forgetting one that I can't think of now, but there is one more. That simply provides the connection between the two so that all the parameters in this physical regime are connected. And then additionally, of course, have the chemistry part. I know what I forgot. Of course, there's the radiative transfer in the physics part as well. That would be the main driver of the dynamics in the first place, because you have heating on one side, no heating on the other side, and this provides the disbalance that would drive your dynamics around the atmosphere in the end, of course. On the chemistry side, there's once again a continuity equation or a conservation of mass equation that includes all the chemical production and loss terms, be that photochemistry, be that deposition, be that kinetic reactions between the different species. And so these you solve as well. And what makes it so complicated is, of course, that you have this grid spherical envelope covering the whole planet. So you don't just solve the equations on one location, but you solve them at many locations at the same time. I hope that answers it a little bit.
Yeah, no, yeah, it sounds like you're solving these physical equations, these kind of Navier-Stokes equations, which are some of the most difficult equations to solve that humanity has ever discovered. And then that's not enough, of course. You end up solving hundreds of, or at least dozens of other equations to describe the chemistry. How different is this, solving it this way from the way that this model is used to figure out, say, the weather that I can expect tomorrow, whether I should get a rain jacket or something?
Yes.
What sort of changes or what sort of things did you have to do to this in order to be able to basically talk about the weather or climate on planets around other stars?
Yeah. So the main change that you do is the one I mentioned, that you change both what star you use to drive everything, and you change the equations that actually describe your orbit of the planet around the star. And that would already allow you quite quickly to move from Earth's climate or chemistry towards any other planets. Now, if you look into weather prediction, that's more a question of scale. So in a sense, you can use this exact same model to do some weather prediction on Proxima Centauri b as well. But the difference between the climate predictions and the weather prediction is just that. Of course, what I show you here, all of these things are quite global scale. So you provide a temperature for one grid box, which covers like many kilometers in space, actually. Whereas if you want to go to weather locally, whether you need to wear your rain jacket in Cambridge today, it certainly was the case in Leuven. I don't know about Cambridge, but that would mean you go to a very high spatial resolution, resolve processes at what I think is sometimes even a couple of 100-meter scale, up to kilometer scale.
And broadening the discussion a little bit with the sort of work that you're doing, considering that you are interested both in questions of habitability and also the questions of the eventual search for life. When you've taken these equations and applied them, what sort of predictions do you have about would this be a nicer place or a worse place to live, or would it depend on where we wanted to live on this particular planet? What does this say about this kind of habitability? And would it be easier to find evidence of life, or harder to find evidence of life on these planets, given what you've discovered?
Yeah, that is a great question that I think can give a very, very long answer. I'll start with the easy example, maybe, that TRAPPIST-1b isn't very likely to be a good candidate there. Proxima Centauri b, well, assuming that anything on Proxima Centauri b is like this, which in itself is a big assumption already, of course, but assuming it is like this, you can look at temperatures as shown over here and say that, well, within this white ring, for example, you have temperatures above the freezing point of water, which is a very crude first estimation of maybe that's a location where you can live. The issue there is, of course, that you're close to this substellar point, and if Proxima Centauri b turns out to be this massively flaring host star that just bombards the planet continuously, then I could imagine it may not be the nicest place to live. On the other hand, if you have a thick convective cloud deck, which we've also shown, that can be quite a protection against stuff. However, if that comes with permanent lightning storms, then maybe it's once again not the nicest location to spend your days, because then the rain jacket might not be sufficient in general. Yeah. So I guess no conclusive answer. But I would say maybe if you move away a little bit from the substellar point here towards middle dayside regions, maybe having some opportunity to walk to the night side at some point as well, because a day-night cycle might be nice in itself. I hope that answers the first part a little bit, and the second part about the biosignature interpretation.
Yeah, and maybe just a way to kind of help focus that particular question. You gave these really nice results about the sort of oscillating behavior that you were able to come up with, the sort of seasonal variations. Is there a way to distinguish between the seasonal variations that are driven by these dynamics and seasonal variations that would be driven by biology? Would there be a nice way to be able to maybe distinguish these, or do you think that this is showing that this is not a good way to go about trying to find life?
I always need to prevent myself from becoming too skeptical when answering these questions, because I do think that this is just one example of a feature that is maybe seen as a biosignature, but that you could quite easily prevent by one other mechanism. And of course, this is just one example of the mechanism that could be used to produce this feature. So yeah, in that sense, it does add some skepticism to a particular biosignature in a sense of a varying feature. However, I think as long as there are multiple ways to prove that the feature you're probing is in some way a biosignature, say that there is seasonal cycles, say that there are chemical species existing together that from a chemical side you wouldn't necessarily expect to exist together. And then maybe I think what would be very nice is I've read about these missions that can at some point maybe resolve planetary surfaces. I think that would be a good thing to include as well, because just from these spectra that are from a single point in space, I think conclusive interpretation will remain quite difficult. Let me say it like that. That's not too skeptical, is it?
No, it'd be wonderful to have spatial resolution, and you've also identified the place for prime real estate. So thank you.
Definitely.
Yeah, I think that concludes my questions.
Thank you.
Thank you, Professor Rimmer, for the nice discussion. And now it's time to move from UK over to the continent. And eventually we are reaching Leuven. And the next member of the jury is Professor Denis Defrère of the Astronomy Unit at KU Leuven. And he is real, he is present in this defense. And he's an expert in the entire process of observational astronomy and focusing on the study of exoplanets. Please. Yeah.
Hey, Marrick, great talk. And it's a really important work, not only to understand the physics of planets, but also in the search for life in the future with mission like life. So I was really pleased to read your manuscript, and I learned a lot. So thank you for that. So I have a first question about the life mission. So let's say we get in 15 years from now, we get a spectrum from life of Proxima b with an infinite SNR on the ozone line, right? So would you be able to retrieve the amount of oxygen in the atmosphere, part one? And part two, would you be able to distinguish between the different mechanism for producing ozone based on this spectrum?
So for part one, I think in the context of Proxima Centauri b, so this would be your goal and target, I think it is not unlikely that we can relate the amount of ozone back to the amount of oxygen in the atmosphere. We've had some discussion about work that actually showed that the ozone feature is saturated. But I think this is the case for planets around solar-type stars, because there has been some recent work that actually focused on varying ozone abundances with depending on how much oxygen you have in it, and you can actually see changing features. Whether this is due to the fact that the ozone feature is not saturated, or I'm thinking if I have a good plot to show this actually. Maybe if I go all the way back. This one. Because ozone is both the photochemically and radiatively active species, if ozone would be present in the stratosphere over here, what it would do is to actually absorb radiation and heat the stratosphere, which could lead to a temperature inversion, which we also see on Earth. Because such emission features of any species relate to the depth in which the species emits, if this pressure-temperature profile changes, then the depth at which your feature originates will change as well. So if you have very tight boundaries on pressure-temperature structure, you know where an inversion is caused, then this will affect the depth of your emission features as well. So maybe this might be, without having the ozone feature saturated or not. This might actually be a way to distinguish how much radiative feedback results from ozone, and in that way, how much ozone you have. And then, of course, you can relate this back through photochemical modeling to how much oxygen you would require for this. So maybe not the easiest endeavor, but I think there is opportunities to get this. Yes. And can you remind me of the second part of your question?
It's a bit related to this. The first question is how would you constrain the different production mechanism of ozone based on that spectrum?
So once again, I think it will require a lot of information on vertical structure throughout the atmosphere. So if you know approximately what the extent of this atmosphere, for example, over here is, you can do this sophisticated modeling with a more or less realistic case if you have some more understanding how much atmosphere there is actually. That would allow you to deduce whether, for example, indeed the stratosphere has this photochemical origin of ozone. So you could deduce that a stratospheric ozone layer would require this, for example. Whereas if you have these variations, I kind of don't want to go through all the slides again, but I will. Whereas if you have these variations with the emission spectra, as a function of time here, of course, many of these are related to the dynamics on the planet, because this would be what drives the ozone feature, for example. So in that sense, you could do something about the dynamical mechanisms on the planet as well. I hope that answers it.
Yeah, thank you. Second question is about the initial condition that you use in most of your thesis. So you assume pre-industrial Earth atmospheric composition. Can you comment on how realistic is this, and how could you derive constraint on initial condition to get another starting point for your simulations?
Yes, yeah, absolutely. So I would say that assumption is by far the biggest assumption of the whole work. Because of course, so having nitrogen in an atmosphere, I think you can say generally that won't be too unlikely, but especially the presence of oxygen is of course a big assumption on Earth relating to the presence of life on Earth. However, there are mechanisms specifically around M-dwarf stars where you can have this accumulation of oxygen in an atmosphere abiotically with, for example, having a large amount of CO2 that is photolyzed by M-dwarf radiation, recombines back into oxygen and actually provides you with an oxygen-rich atmosphere. So well, let me just say it like that. There are abiotic ways to having a lot of oxygen in your atmosphere as well, which on the other hand is not a great conclusion for the search for life elsewhere, once again, of course. But that's a different question. But I think, yeah, of course, having a better knowledge of what actually to provide for initial conditions would be a fantastic starting point for any photochemical modeling. And I think from the models of planet formation theories, we should get some input on maybe relating to what a stellar composition is. You can relate that to what the composition of a protoplanetary disk is. And maybe from that have some very crude estimates about what a planet would be made up of. But of course, that's, especially for rocky planets, is quite a challenge because it will be affected by surface processes over long time scales quite substantially.
Yeah, it's definitely a whole area on research to connect the condition to planet formation, but it's I think really fascinating.
Yes.
All right, maybe a naive question on my side. For Earth, do we know the fraction of ozone produced by lightning compared to UV radiation, and how does it compare to, let's say, TRAPPIST-1D?
So for Earth, it's actually quite small, I think. I don't have the exact numbers in mind. But I think so that on Earth, indeed, there's production of ozone due to lightning, which you say correctly, which is a tropospheric process that involves many other species. I don't have this production of ozone because I don't have all the other species, but what instead nitrogen oxide in this case will do, and what it also does in the stratosphere on Earth, is to provide this catalytic cycle. Now the comparison for TRAPPIST-1D, I do have some extra slides, just a few. A few too many, maybe. There we go. So here you can see the comparison between Proxima Centauri b lightning flash rates and TRAPPIST-1D lightning flash rates, where you can actually see that the TRAPPIST-1D lightning flash rates are orders of magnitude higher, which is actually related to the fact that TRAPPIST-1D is a lot smaller, has a lower gravity, affecting the scale height of the atmosphere, and therefore your cloud structures will, in terms of kilometers, will be a lot bigger. And because you use clouds in terms of kilometers to deduce the lightning flash rates, you get this enhancement of lightning flash rates on TRAPPIST-1D, which is then once again a consequence of the fact that we use this Earth-like parameterization. So the comparison, it kind of seems to illustrate that because Proxima Centauri b in our simulations is so similar to Earth. Maybe that's somewhat valid over there, but I wouldn't trust the lightning flash rates on TRAPPIST-1D over here.
All right, thanks a lot. No more questions from me.
Thank you.
Thank you, Professor De Vreer, for the discussion. And Marrick, during your PhD, you served 2 masters, one in Edinburgh and one in Leuven. In Edinburgh, it was Professor Paul Palmer, who is the director of the Center for Exoplanet Science and the science director of the National Center for Earth Observation. And here in Leuven, it is Professor Leen Dessin, and she's the director of the Institute of Astronomy of KU Leuven. Now, I can't imagine that it has been sometimes not the easiest life of a PhD student to satisfy both, but I think you managed quite well. And now is the moment for the 2 promoters and supervisors to ask some burning questions they still may have. So first I would like to ask Professor Palmer, do you have still some questions you would really need to ask right now to Marrick? Hello?
Hello. No,
I
I have no more questions. Marrick has been a fantastic scientist and has done a fantastic job doing his research. I have no further questions.
Thank you very much. Professor Dessin? Yes.
Hi, Marrick. Thanks a lot also for a very nice talk and already the answers to the questions. You have also acknowledged in your words in the time when you were thanking us is that we often went into very basic discussions when you were in my office. And I would like you to give me an answer on a very basic question I have since what we are after, what Paul has been asking you, and also you had also such a question already from my colleague, Professor De Vreer, is how do we understand the mathematics and the physics and why are equations the way they are? And so you are only at slide 2 when you have given us there that one equation on the synchronization time. And so we see a very easy analytic equation, but it's not that way. How has that equation that you have been used to estimate the synchronization times, how has that been calculated and what does it tell us?
I would argue that this is not necessarily a basic question, but I'll do my very best. All right, so I'll just show the equation itself. It's this one over here. So I doubted whether I should include it. Now I do regret having included it, but we shall try to get through it. So I know this factor. Okay, let me go first to other factors before going to that one. So I think what this comes down to, the derivation, is of course, at the very basic, the gravitational interaction between the planet and the host star. And we had some discussion about this during the internal Viva in Edinburgh as well, of actually where would a factor r to the power 6, for example, come from. But so it seems that for synchronization to happen, you would need a varying gravitational field over the planet structure itself. So you'd have one amount of gravity at the point closest to the star, one amount of gravity at the point farthest away from the star, which would lead to slowing down the orbit to match the slowing down the spin to match the orbit around the planet. And I think this is where the to the power 6 of the orbital distance comes from. The stellar mass, of course, is due to the gravitational interaction. That may be the easiest. The planetary density in itself, this would be, I guess the radius part inside the density would come from the fact indeed that you have varying gravity across the planet. And then the mass itself would be, of course, what's providing your gravitational interaction between the two. The spin, this omega over here denotes the spin of a planet, and this is just an initial spin factor. So if it spins like Earth, for example, and then this, so this is just a constant factor to spin down from a specific spin to the orbital rate. And in the calculations here, I just used Earth's current spin rate because we don't know them for exoplanets. Then I specifically left those parameters over here for last because these are the love number K2 and the Q parameter, which I don't think even has another name, which give you, or not necessarily me too much, but give other people information about the interior structure of a planet. Because I think the love number indicates the rigidity of a planetary body, whereas the Q parameter gives you the rheology of a planet. I don't know exactly, I have to admit, I don't know exactly what these terms mean. All I know is that it accounts for the interior structure of a planet. And then this factor in front of it is just all the unit conversions by, I think this tidal locking time scale is given in years in the end. So it includes, for example, the years to second and the stellar mass in solar masses conversion. I hope that is a somewhat satisfying answer.
Yeah, it is. I also recommend you talking to Mats, who has been working on tidal effects.
That's a great idea,
and
actually.
He has a very good idea on why the Earth power 6 is there, since he has it also in his equation.
Cool. Okay. Yeah, I should have done that last week already.
You're welcome.
Thank you.
Thank you, dear supervisor. Last but not least, this is a public session here. That means now it's a moment that you can ask what you ever wanted to know about exoplanets and ozone and transport phenomena in atmospheres. So, are there questions? No questions, so you did a very good job.
Good.
So, in proxy, I have one talking about tidal locks. How big is the chance that the Earth is going into tidal lock, considering that the moon is slowing it down? I don't think I would like that. But yeah, well, just knowing.
Yeah, no, I don't think I would like that either. Just thinking.
I thought that was an easy question. I'm sorry.
No, that's fine. I think it's an interesting question. but no, not necessarily an easy one for me. I don't think the tidal locking state would be very likely. Because I think even if the Earth would be slowed down completely to the moon's rotation, it would still be, 30 days that you have remaining, which still allows for multiple spins in 1 year, basically.
That is a relief. And I thank you for that. And now it's time for the jury to withdraw. And I would like to invite also the online jury members to join us in the private session. And we will decide on your verdict.
same hands, and then I refer to what the chairwoman just have been telling us. We are scientists, and we have to act as scientists, and this implies trying to avoid things to be used in a black box. They should become gray boxes, and if possible, white boxes, so that we really can understand what is happening. And we have tried to do that during various discussions. I liked it. I hope you liked it as well, you know, since it was also for me enlightening, trying to understand, you know, why other people have been acting differently than what we have been doing. And so it improves our knowledge from all sides. I think, and maybe also Paul, I don't know, if Paul Palmer, your other supervisor, is not here. He has an extremely bad Wi-Fi connection, so I'm not sure whether he can say you something, you know, at this current stage, but I think I am entitled to also thank you in his name for being such a good PhD student and for being able to connect both of us, since, you know, these are this kind of a shared PhD projects, and they ask also quite a lot of communication, since we have to go together to some path. I have a very small present for you with me. I know you like hiking a lot, and we have been discussing that from time to time, but it's only very small. I just advise it that you have it with you always. I hope you don't need it. When I'm hiking, I always need it, but I have something which is called a non-talent, of which I hope you will have much more talent than I have. It is hidden in this very small box.
Thank you.
It's just a very small present to thank you for all the years that we have been collaborating.
Thank you so
and
much.
I wish you a very bright future. Thanks.
Thank you so much, Lane. And thanks for all the guidance as well. Now everyone's curious, huh? Amazing. Thank you so much. And very timely, actually. The other one was broken, so it's perfect. Thank you so much. My final word. Okay, I have not prepared anything, as you may realize. But I would like to say a big thank you to all of you for coming, because I know it may be kind of strange that I've been away from Leuven for a time, like I was only here in 2022, and sometimes comes back for a week or not randomly and shows up and meets some people in the corridor. But so I appreciate that you all still took the effort to come to my public defense here. And I want to say that it was a delight to be in Leuven in the first place. I thanked Paul and Lean already for their guidance over the years, but could not have done it without you. And a big thank you has to go to Jeremy, who's in the room, and Professor Ken Rice as well, who's not available today, for co-supervising the project and ensuring its adequate process. And lastly, to all the jury members, thank you for ensuring this smooth process as well. And it was quite a pleasure from my side to stand here as well. Thank you so much. Thank you. Glad to hear that.